Hello viewers, whenever we look around us, we find different things. These things could be of different shape or they may be of the same shape. Let's have a look at these leaves. Now these leaves, by just looking at them, you can say that they are different leaves, and obviously you can make out that they have been picked from the different plants. But if the leaves have been picked from the same plant, then how do they look like? So these are the leaves which have been picked from the same plant. What do you observe here? We find that these leaves have almost identical shape, but their sizes are different. Now just as we talk of leaves, in the same way we can talk of geometrical figures too. Now all the closed figures over here, they are polygons, and by just looking at them you can very well make out that they are of the different shape. But if the polygons are of the same shape, then how do they look like? Here are two triangles. In these triangles, triangle ABC and PQR, the side AC is 8 centimeter, side AB is 10 and BC is 11, and for the triangle PQR, this side is 8, PQ is 10 and QR is 11. So that means these two triangles have the same shape and they have the same size. But if the triangles, or for that purpose any polygons, have different shape but different size, then obviously they will be different. But in case they have the same shape but different size, then let's have a look at these two triangles. Now these two triangles, both obtuse angle triangles, both are having the same shape, with base angle over here A as 110, this 110, but this side is side AC 6 centimeter, side PR is 12 centimeter and side AB 4 centimeter, side PQ is 8 centimeter. So here they are of the same shape but they are of the different sizes. We are showing you another picture. You decide for yourself whether they are of the same shape or not. The figures are here. Here these two figures, they are, what do you observe? They are of the same shape, but this figure is larger in size than this figure. This figure is larger in size than this figure. So such figures which have the same shape but different size are called similar figures. So what do we say about similar figures? Similar figures have same shape but their size may be same or it could be different. But by just looking at the figures, it becomes problem for us to decide that whether they are of the same shape or not, because looking at the figures could be deceptive at moments. So for that purpose, in case the two polygons have to be similar, there have to be two conditions which must be satisfied simultaneously. The first condition being the corresponding angles of the polygons are equal and the corresponding sides should be proportional. So let's have a look at two rhombus. Now in this quadrilateral, this side is 16 and in this one it is 8. Ratio of these two sides is 16:8, that is 2:1. Now the sides of this figure are all 8 centimeters and that of the bigger one are all 16 centimeter. So here we find that the ratio of corresponding sides, that is this to this, is 2:1. Similarly the ratio of this is to this is again 2:1 and the ratio of this is also 2:1. Now let's have a look at the corresponding angles. To this angle, the corresponding angle is this. Let's see. What do we find? They are equal. And to this angle, the corresponding angle is over here. Let us see the measure of this angle. These two angles are also equal. Looking at the third angle, this and this, they two are equal. So, in these two figures, we find that the corresponding sides are proportional, the ratio being 2:1, and the corresponding angles are also equal. But if I distort this figure a little bit, here although the ratio of the sides has still remained same, but the angles have changed. So, can we now say that this figure is similar to the figure outside? No, these are not. So, that means we find that for two figures to be similar, we have to have two conditions. The first being the corresponding sides should be proportional and the corresponding angles have to be equal. Let us have a look at these two figures now. Now, here both the hexagons have each angle as 120 degrees. A, P, B corresponds to Q, C corresponds to R, R to C, and each D here to S, S to D, E to T, and T to E. Each angle of this polygon is 120 degrees, and so is each angle of this polygon. But the side AB of this is 6 centimeters and side PQ of this is 6 centimeters, and the side AF 6 centimeters and PV is 6 centimeters. Have a look at the sides again. The side AB of this hexagon is 6 centimeters and the side PQ of this hexagon is 8 centimeters. The side AF is 6 centimeters and the side PV is 6 centimeters. So, if we happen to take the ratio of side AB to PQ, that is 6:8, but the ratio of side AF to PV is 6:6. Now, in these two figures, though the corresponding angles are equal, but the corresponding sides are not proportional, so we can say that these two hexagons are not similar. So, that was the one thing. Let us take another case where the sides are proportional now. Here the two figures are this and this. The side of this is 8 centimeters and the side of this rhombus is also 8 centimeters. Now, this one being a square will have each side as 8 centimeters and each angle will be 90 degrees. But how about this? This is a rhombus ABCD. Here the sides are all equal, that is 8, but the angles are different. Corresponding to angle E is angle A. Angle E is 90 degrees, but angle A is not. So, here we find that the ratio of the sides is same, but the angles are different. Hence, we can conclude that these two figures are also not similar. So, we see that when the two polygons are similar, we need to have two conditions which should be simultaneously satisfied. The first, the corresponding sides should be proportional, and secondly, the corresponding angles must be equal. Now, let us take a triangle, and in this triangle PQR, I am constructing a side parallel to QR. For this, we will keep the set square like that, covering this side, and then the set square may not get disturbed, we will hold it with this scale and keep on moving it up. So, here when I draw the line, this line is parallel to this line. Let us measure these two segments, naming this point as A and this point as B. Here PA is 3 centimeters and AQ is 6 centimeters. Seeing the other two segments, the segment PB is 5 centimeters and BR is 10 centimeters. Let us find the ratio of the segment PA to segment AQ. This ratio is 3 upon 6, that is equal to 1 upon 2, and the ratio of segment PB to BR is also 5 upon 10, that is equal to 1 upon 2. So, what we have seen here, that when we draw a line parallel to this side to intersect the other two sides, then it divides these two sides proportionally. Now, this result was established by a Greek mathematician Thales, and according to Greek mathematician Thales, this theorem states like this: in a triangle, a line drawn parallel to one side to intersect the other sides in the distinct points divides the two sides in the same ratio. So, let us take a triangle and prove the Thales theorem in a formal way. Now, here is a triangle ABC and the line DE is parallel to the side BC. Now, I need the area of triangle ADE. For that, I will draw perpendicular from E on AD. And let us take the other triangle as EBD. So, area triangle ADE is 1 by 2, its base is AD and the height is, let us name that point as F into EF. And how about the area of triangle DBE? Its base is DB and the height is same as that of triangle ADE, that is equal to EF. This common factor EF and EF cancels out, half and half cancels out. So, we find that the area of triangle ADE is to area of triangle BED is AD upon DB. Similarly, area of triangle ADE can also be written as AE upon area of triangle EDC that will be AE upon EC. But the triangle BED and CEB, they are on the same base, that is ED, and they are between the same parallels, these two. So therefore, area of triangle BED will be equal to area of triangle CEB. So from there, what do you find? Because area of triangle BED is equal to area of triangle CEB, therefore from there AD upon DB, that becomes equal to AE upon EC. So that was the proof of Thales theorem. I'll repeat that theorem again, that in case a line is drawn parallel to any side of a triangle to intersect the other two sides, then it divides the other two sides proportionally. Now here in this figure, again triangle ABC is there and DE has been drawn parallel to the side BC. So according to Thales theorem, what do we get? AD upon DB equals AE upon EC. If I add 1 to both sides, 1 plus AD upon DB equals 1 plus now DB plus AD, that is nothing else but AB upon DB. And how about AE plus EC? That is equal to AC upon EC. So that is the result we have derived from the Thales theorem. Now let's have a look at another problem. Here in this problem, triangle PQR is there and ST is the line which is drawn parallel to QR. So by Thales theorem, we can say that PS upon SQ, that is equal to PT upon TR. And here we are supposed to find out the value of x. Substituting the corresponding values, we get 4 upon x minus 4 equals x minus 3 upon 3x minus 19. To solve this equation, we cross multiply them, we will get 4 times 3x minus 19 equals x minus 3 times x minus 4, which on simplification will give you the equation x square minus 19x plus 88 equals 0, and from there we will get the values of x as x minus 11 as 0 or x minus 8 as 0. These x minus 11 and x minus 8 being the factors of this quadratic equation, and from there we get the value of x as 11 or 8. Let's take another problem, and the problem is a triangle ABC in which angle A is equal to angle B and AD is equal to BE. Let's mark them. Angle A is equal to angle B, that is given to us, and AD is given equal to BE. And now we have to show that DE is parallel to AB. Now, in case I want to show that DE is parallel to AB, what I need to show is that CD upon DA is equal to CE upon EB. Angle A is equal to angle B. So, therefore, AC will be equal to BC, because these are the sides opposite to equal angles, and we are already provided that AD is equal to BE. On subtracting these two results, we find that AC minus AD is equal to BC minus BE. Now, AC minus AD is nothing else but CD, and BC minus BE is equal to CE. If I name this equation as 1 and this result which I have calculated as 2 and divide 2 by 1, I get CD upon AD is equal to CE upon BE. So, that shows that the side DE is dividing these two sides in the same ratio. So, hence by using converse of Thales theorem, we can say that DE is parallel to AB. So, here we use the converse of Thales theorem to establish a very important result in the case of a triangle. Now, here we are again having one more problem for you. In the triangle ABC, AD is the bisector of interior angle A. We have to prove that AB upon AC is equal to BD upon DC. For that, we need to do a bit of construction. I will extend this AB and cut off from this A point a length equal to AC. Let us name this point as F and join F to C. Now, here this side has been constructed equal to this side, that is AC is equal to AF by construction. So, therefore, angles opposite to this side, this angle, if I name this angle as 1 and this angle 3, so angle 1 will be equal to angle 3. Also, AD is the bisector of angle ABC. So, if I name this angle as 2 and this angle as 4, angle 2 will be equal to angle 4. Considering the triangle AABC, here CAB is the angle whose bisector AD has been taken, and if we consider the triangle ACF, its side FA has been produced to B. So, therefore, angle 2 plus 4 has to be equal to angle 1 plus angle 3. Why so? Because the exterior angle is equal to the sum of remote interior angles, and to this exterior angle the remote interior angles are 1 and 3. Angle 2 and 4 are equal. So, for that I can write 2 times angle 4, and angle 1 and 3 are also equal. For this I can write 2 times angle 3. So, that gives me angle 4 is equal to angle 3. But angle 4 and 3, they are making a pair of alternate angles with side CF and DA. So hence we can say that CF is parallel to DA because the alternate angles are equal. Now if we apply our Thales theorem once again, we find here that to side CF, AD has been drawn parallel. So therefore, BA upon AF is equal to BD upon DC. But AF is equal to AC by our construction. So we can replace this AF by AC and we get our desired result. So today we learnt about the similar figures and learnt about some basic proportionality theorem. Now the similarity in triangles is of significant nature, and about this we will talk